All right, welcome. In this video, I'm going to be telling you about the fundamental theorem of calculus. And in this video specifically, I'm going to be showing you how to take a definite integral. Now, in the last video, we talked about some definite integrals. That's what this would be, a definite integral. And then at some point in the previous unit, we talked about indefinite integrals. I think it was Unit 5, Lesson 2, where we talked about antiderivatives. And so this is what we would call an indefinite integral. And just to kind of remind you, okay, in the last lesson, we learned really about the meaning of the definite integral. It's the amount of area under the graph of y equals, in this case, 2, between x equals 1 and x equals 4. So it was equivalent to the area of this rectangle, which had height 2 and length 3. So I said that that integral was equal to 6, just because that was the amount of area in here. But then, a couple weeks ago now, we said that we found the antiderivative of x to the fourth minus sine of x with respect to x by, we'll use the power rule. Increase the power by 1, divide by the new power. And a derivative for negative sine, or an antiderivative for negative sine of x would be positive cosine of x. And then we needed to remember to add the plus c. So the natural question is, why are we using this integral symbol for both problems? What is the connection between an antiderivative problem and an area problem? And that's what we're going to learn about. But before I tell you about the fundamental theorem, I do need to give you like a formal definition of the integral. Last time we said that the integral from a to b of f of x dx represented the amount of area underneath the graph of f, but I gave no way to actually compute that. And so what it really is the limit of the Riemann sums. It's the limit as that thing that looks like the absolute value of a triangle. That's the norm of the partition. That means the width of the widest rectangle in our Riemann sum is going towards 0, which then necessitates that there's an infinite number of rectangles. That's going to be the actual true value of the exact area under the graph of f. But what you need to know is that the integral is the limit of a Riemann sum. Just in some world where you've got Riemann sums and you want to take the limit of them as you can take more and more rectangles and they're smaller and smaller rectangles. And this is the concept of Riemann integration. So the big idea with the fundamental theorem of calculus is kind of this dual representation of the same concept. So suppose I've just got to get away from you kids, right? I just need to put some physical distance between us for the weekend or something like that. Just had enough. And so what I'm going to do is I'm going to get in my car and I'm going to drive on a straight track, of course, because it's AP calculus. I'm going to drive on a straight road for 2 hours at 70 miles. And you would know that that would give us 140 miles of distance between us, which I feel like is just the right amount. Alternatively, I could have been, not paying attention to my speed, and it's just like, I just need to go and I need to get 140 miles away. And so if I knew that I had started at mile marker 234 to mile marker 374, that would be telling me the same information. Both of these things are telling me that the distance I traveled was 140 miles. So in terms of calculus, we have seen, maybe you have, maybe you haven't, maybe you saw it in physics class, that the area under the graph of a velocity function is going to give us a change in position. So what I'm proposing here is that the integral from 0 to 2 of 70, constant velocity of 70 with respect to t, well, we would know how to find that. It's equivalent to a rectangle, right? That's equal to 140. It's a rectangle with height 70 and width 2. But then, on the other hand, I could say that my position at time 2 hours minus my position at time 0 hours when I set off on my journey was equal to 374 minus 234 is 140. So both of these things are 140. And so what you want to think of is, kind of like what's the relationship between velocity and position. What is position to velocity? If you think about it, what I've done here is I've got an antiderivative. Okay. So what I'm telling you, the fundamental theorem of calculus is telling you, is that the definite integral is related to a net change in the antiderivative. Okay, so the actual fundamental theorem of calculus, as we're taking it in this course, is that if f prime is a piecewise continuous function for x between some numbers like a and b, then the integral from a to b of f prime of x dx is equal to f of b minus f of a. It's again related to a net change in an antiderivative. This is giving us, kind of implying a three-step process for taking integral. So your first step is always going to be find an antiderivative. Then once we find an antiderivative, we're going to plug in the balance of integration, that a and that. And then once we've found an antiderivative and plugged in our balance of integration, we are going to subtract. And much like, when we were learning how to solve separation of variables, differential equations, or just learning how to take derivatives, this is the type of thing that we just need to practice a bunch and we will get good at with time. And so let's do a nice old-fashioned algebraic example. And this is the type of example that, if you were in an introductory calculus course 100 years ago, it's probably where we would have started, right? Draw a picture of a graph, find an antiderivative by hand, compute the integral. So we can draw a picture of y equals x squared plus 1. Maybe it looks a little like that. I don't know. That might not be the best drawing ever, but it'll work. Okay, and maybe we'll say that this right here is 2. The figure might not be drawn to scale, but that's all right. And so the area that we're hoping to find the exact value of is going to be right here. Okay. And what we will do is I'll say, well, I'm going to first find an antiderivative for x squared plus 1. An antiderivative for x squared is increase the power by 1 and divide by the new power. And an antiderivative for 1 with respect to x will just be 1x. Okay. Maybe you're thinking, maybe I need a plus c there. And yeah, I don't know, maybe you do. Okay, so maybe I'll throw in a plus c. Okay, so that's step 1, find an antiderivative. Okay, to indicate that we are going to be finding the net change of this antiderivative from 0 to 2, we oftentimes will put a little vertical bar and put a 0 and a 2 there, which basically says I'm planning to plug in 2 and plug in 0 and subtract and see what the difference was. Okay, so now I'm going to plug in the 2. So 1/3 of 2 to the third is 1/3 of 8. That's 8/3. Plus 2 plus c, c can be any constant, I guess, minus, over here, when I plug in 0, I get 1/3 of 0 to the third is 0, plus x is 0, plus c. Okay, and when I actually do that subtraction, I'm going to get that 8/3 plus 2 plus c minus c, and the c's will subtract away. And I'll get 8/3 plus 2 is going to be 6/3, is going to be 14/3. So the other thing that I want to tell you is that the plus c is unnecessary. That what's happening here is that kind of up above, we said find an antiderivative. And that can be any antiderivative, right? So when I go down here and I'm trying to work this problem, I can choose the antiderivative with the c equals 0. And so moving forward, that's what I'm going to be choosing, right? We don't need to use the plus c in a definite integral. That's what you're going to remember. Okay, but that's how we did. Found the exact value of the area under the graph of y equals x squared plus 1 between x equals 0 and x equals 2. Now I want to show you about some table problems. And these are actually really friendly to us if we just, can internalize that three-step process, right? Because you just start by thinking to yourself, what's an antiderivative for f double prime of x? What's a function? If I take its derivative, I'll get f double prime, and that would be f prime. So I know that the first step antiderivative is going to be f prime of x. And we're going to let x run from 2 to 5. Okay? And that means that I've got f prime of 5 minus f prime of 2, which is two numbers I can just look up from the table, and that's going to be negative 3 minus negative 1. And that feels to me like negative 2. Okay. But we can, kind of ramp up the difficulty on this a little bit. I could add in like a constant or something and say find the integral from 3 to 8 of 3f double prime of x plus 4. And that would just add a little bit on there. So what would happen would be, I'll go and I'll find an antiderivative for 3f double prime. That will be 3f prime. An antiderivative for 4 with respect to x is going to be 4x. And we're going to let that run from 3 to 8. So I might say that that's 3 times f prime of 8, so that's 3 times negative 7, plus 4 times 8 is 32, minus what happens when I plug in 3. 3 times f prime of 3 is 3 times negative 4 is negative 12, plus 4 times 3 is 12. Okay, so, we can figure out what that was. I feel like that's going to be negative 21 and 32. I think it's going to be 11. Okay, but I think that'll be far enough for us. Now, before we move on, I do want to bring you back to a situation that we talked about in the last lesson, right? If we have kind of backwards bounds of integration. Last time we basically that if we reverse our bounds of integration, then it may go negative. But in terms of the fundamental theorem of calculus, we can pretty quickly see why this is true. What I'm going to do, I'm going to go over here and I'm going to run the same process. Now realize that this is the backwards integral, and I found that the integral from 2 to 5 was equal to negative 2. Okay, so hopefully this is going to come back positive 2. So this is going to equal, antiderivative is going to be f prime. So f prime of 2 minus f prime of 5. And then the other one I had f prime of 5 minus f prime of 2. So you're starting to see why it's going to be the opposite. F prime of 2 is negative 1 minus f prime of 5 was negative 3, and that's equal to 2. So I thought I'd just point that out right while we were here looking at a table. I think that makes it the easiest to see. Now, the last thing I want to tell you about in this video is the average value of a function. You all are very familiar with how to compute an average of, a collection of numbers. You add them all up, and then you divide by how many numbers you got, right? And the idea of the average value of a function is going to be very similar. So what we're going to do is we're going to add up all the values of the function, which would be hard because, right, if it's a continuous function, there's going to be a whole lot of different values. But we've seen that an integral is, at least corresponds to the idea of a sum. So it wouldn't be unreasonable for me to say, wait, I'm going to just add up all of the area under the graph of the function. And then I'm going to divide. I can't divide by the number of data points I've got because it's a continuous function. I've got an infinite number of data points. But I could, since I'm taking an area, I could divide it by the width of the interval, and I could get the average height. So that's what we're going to do. We're going to add them all up and then divide by b minus a. Okay. And this is a pretty common thing to happen in AP Calculus. They'll ask you about the average value of a function. So I've got a couple examples for you. So let's just do a couple of algebraic examples. And let's find the average value of cosine theta on the closed interval 0 to pi over 2. And just to kind of remind you of what that might look like, y equals cosine x. Okay, that's going to start up here. And I think that, okay, because cosine of pi over 2 is 0, yeah, that's what we're going to be looking at. That was a pretty rough graph there. Maybe I can get it a little smoother. Right, because we know it's going to, eventually come back up like that, but we don't really care because this is 0 to pi over 2. That'll be good enough for us. Okay. What I really need to do is I need to say 1 over pi over 2 minus 0 times the integral from 0 to pi over 2 of cosine x dx. And we just learned how to compute that integral on the right. We're going to start by taking an antiderivative for cosine of x, and that would be sine of x. And so that's 1 over pi divided by 2 times sine of x as x runs from 0 to pi over 2. Right, just thinking on a unit circle level. Okay, here sine of 0 is the y-coordinate there. That's going up here. Pi over 2, sine is the y-coordinate up there. That's going to be 1. So I've got 1 over pi over 2, which is like 2 over pi, multiplied by sine of pi over 2 is 1, sine of 0 is 0, and I get that that average value is 2 over pi, which is, a little less than 2/3, and so, it seems maybe reasonable. It's definitely somewhere in there. That's all I've got to say for that example. All right, now maybe you can try this one on your own. Average value of the square root of x on the interval 1 to 16. I'll help you set it up, but then after that, I think I'm going to have you try. So this is going to be 1 over 16 minus 1 times the integral from 1 to 16. I'm not sure what happened here. Times the integral from 1 to 16 of square root of x dx. But I know if I'm going to integrate that, it's going to involve an antiderivative, and if I'm going to differentiate square root of x, I'm better off to write it as x to the 1/2 power anyway. So this is 1/15 of, x to the 1/2, I'm going to add 1 to the power. That's going to be 1/2 plus 1 is 1.5, or 3/2, divide by the new power. And I'm going to let x run from 1 to 16. Now, something that we can do if I've just got kind of one term in my antiderivative is that I could factor, it's going to be 2/3 of 16 to the 3/2 minus 2/3 of 1 to the 3/2. I can factor out the 2/3. And so I think I'll do that. I'll say that that's 2 over 15 times 3 is 45. And so this will be 16 to the 3/2 minus 1 to the 3/2. Now 1 to the 3/2 is easy enough to compute, right? It's 1. Any power of 1 is 1. Any real power of 1 is 1. But 16 to the 3/2, what I need to do over here is say, okay, 16 to the 3/2 equals the square root of 16. Do the half power first, then take that to the third power. So that's 4 to the third, which I'm feeling like is going to be 64, yeah. Okay. So I can say that this is 2 over 45 times 64 minus 1. So it's going to be 63 times 2. 7 times 9 is, oh, wait a second, hold on. Because 63 is 9 times 7. And 45 is 9 times 5. So I've got 14 over 5 as my average value. All right, so let's look at one with a graph. So suppose I've got g, which is, a piecewise continuous function. I guess it's a continuous function at all x. And it is given by 2 line segments and, a bit of curve. And, maybe I don't know. That's going to be a perfectly fine curve. And if they tell us that the average value is, I think that was supposed to be 3.1 when I was copying the problem. Yeah, that's what I want to be. That's going to be 3.1. What is the value of the integral from 3 to 8 of g of x dx? That's the idea. And again, if what I'm searching for is the integral from 3 to 8, that's going to be this amount here, right? The highlighted in blue area is what I'm hoping to find eventually. So what it has told me in the statement of the question is that the average value is 3.1. So that means that 1 over 10 minus 0 times the integral from 0 to 10 of g is going to be 3.1. That tells me that the actual integral from 0 to 10 of g is going to be 31 if I multiply both sides by 10. Okay, so that means that if I add up the areas of these rectangles plus the blue area, I'm going to get 31. And so this first rectangle has a width of 3 and a height of 2, and so that's an area of 6. And then the other one has a width of 2 and a height of 5, so it's going to be an area of 10. Looks like it's not going to be exactly drawn to scale. That's okay. That means that 6 plus area A that I'm trying to find, so 6 plus A plus 10 needs to equal that 31. Okay, so that's telling me that the area A that I'm hoping to find is going to be 15. And in conclusion, I will say that the integral from 3 to 8 of g is going to equal, what is it going to equal? 15. Okay. Could have extended this question a little bit and asked for, like, okay, if this is the average value on all of 0 to 10, what's the average value on 3 to 8? And then it would have been 3. Okay. But I think that'll be good for this problem, and I think that'll be good for this video. So thanks for watching.